Hello everyone, this is the remaining part of Aldehyde, Ketones and Carboxylic Acid audiobook. So let's start. Carboxylic acid, carbon compounds containing a carboxyl functional group COOH are called carboxylic acids. The carboxyl group consists of a carbonyl group attached to a hydroxyl group, hence its name carboxyl. Carboxylic acid may be aliphatic, RCOOH, or aromatic, depending on the group, alkyl or aryl attached to carboxylic carbon. Large number of carboxylic acids are found in nature. Some higher members of aliphatic carboxylic acid, C12 to C18, known as fatty acids, occur in natural fats as esters of glycerol. Carboxylic acids serve as a starting material for several other important organic compounds such as anhydrides, esters, acid chlorides, amides, etc. 12.6 Nomenclature and structure of carboxylic group. 12.6.1 Nomenclature. Since carboxylic acid are among us the earliest organic compound to be isolated from nature, a large number of them are known by their common names. The common names end with the suffix -ic, acid, and have been derived from Latin or Greek names of their natural resources. For examples, formic acid, HCOOH, was first obtained from red ants. In Latin, that is formica means ant. Acetic acid, CH3COOH, from vinegar, Latin acetum, means vinegar. Butyric acid, CH3CH2CH2COOH, from rancid butter, Latin butyrium, means butter. In the IUPAC system, aliphatic carboxylic acids are named by replacing the ending E in the name of the corresponding alkane with oic acid. In numbering with the carbon chain, the carboxylic carbon is numbered 1. For naming compounds containing more than one carboxylic group, the alkyl chain leaving carboxyl groups is numbered and the number of carboxyl group is indicated by adding the multiplicative prefix dicarboxylic acid, tricarboxylic acid, etc. to the name of parent alkyl chain. The position of COOH groups are indicated by the Arabic numeral before the multiplicative prefix. Some of the carboxylic group acids along with their common and IUPAC names are listed in the table 2.3. Here you can see the table 12.3 names and structure of some carboxylic acids. Structure here you can see, and the common name and their IUPAC name I am reading. Formic acid, methanoic acid. Acetic acid, ethanoic acid. Propionic acid, propanoic acid. Butyric acid, butanoic acid. Isobutyric acid, 2-methyl propanoic acid. Oxalic acid, ethane dioic acid. Malonic acid, propane dioic acid. Succinic acid, butane dioic acid. Glutaric acid, pentane dioic acid. Adipic acid, hexane dioic acid. Tricarboxylic acid or carboxylic acid, that is propane 1, 2, 3 tricarboxylic acid. Benzoic acid, benzene carboxylic acid. Phenylacetic acid, 2-phenyl ethanoic acid. Phthalic acid, benzene 1, 2 dicarboxylic acid. 12.6.2 Structure of carboxyl group. In carboxylic acids, the bonds to the carboxyl carbon lie in one plane and are separated by about 120 degrees. The carboxylic carbon is less electrophilic than carbonyl carbon because of the possible resonance structure shown below. Here you can see that structure. Now 12.7 Methods of preparation of carboxylic acids. Some important methods of preparation of carboxylic acids are as follows. Number 1. From primary alcohols and aldehydes. Primary alcohols are readily oxidized to carboxylic acids with common oxidizing agents such as potassium permanganate in neutral, acidic or alkaline medium, or by potassium dichromate, that is K2Cr2O7, and chromium trioxide, that is 3RO3, in acidic media, and it is also known as Jones reagent. Here you can see the both reaction. RCH2OH in presence of alkaline KMnO4 forming RCOOH, and CH3 CH2 whole 8 CH2OH, that is 1 decanol, and in the presence of Zone's reagent CH3 CH2 whole 8 COOH decanoic acid it is forming. Carboxylic acids are also prepared from aldehydes by the use of mild oxidizing agents. Number 2. From alkyl benzenes. Aromatic carboxylic acids can be prepared by vigorous oxidation of alkyl benzenes with chromic acid or acidic or alkaline potassium permanganate. The entire side chain is oxidized to the carboxyl group irrespective of length of the side chain. Primary and secondary alkyl groups are oxidized in this manner while tertiary group is not affected. Suitably substituted alkenes are also oxidized to carboxylic acid with these oxidizing reagent. Here you can see both reaction in which the benzoic acid is the last product. Number 3. From nitriles and amides. Nitriles are hydrolyzed to amides and then to acids in the presence of H ion or OH ion as catalyst. Mild reaction conditions are used to stop the reaction at the amide stage. Here you can see the reaction. RCN is forming RCOOH and the intermediate product is RCONH2. And here then after ethanamide, that is CH3CONH2 is forming ethanoic acid plus NH3 on heating, and benzamide on heating it is forming benzoic acid and H3O ion and plus NH3. H3O ion presence is there. 4th, from Grignard reagents. Grignard reagents react with carbon dioxide, dry ice to form salts of carboxylic acid, which in turn give corresponding carboxylic acids after acidification with mineral acid. Here you can see this reaction RMgX plus OCO and forming it is RCOOMgX, and in the final product is RCOOH. As we know, the Grignard reagents and nitriles can be prepared from alkyl halides, and for this you have to refer the unit 10 in class 12th, and the above methods are useful for converting alkyl halides into corresponding carboxylic acids having one carbon atom more than that present in alkyl halides, ascending the series. 5th, from acyl halides and anhydrides. Acyl chlorides when hydrolyzed with water give carboxylic acids or more readily hydrolyzed with aqueous base to give carboxylate ions which on acidification provide corresponding carboxylic acids. Anhydrides on the other hand are hydrolyzed to corresponding acids with water. Here you can see the reaction, and in this reaction benzoic anhydride is converting into the benzoic acid, and benzoic ethanoic anhydride is forming the benzoic acid plus ethanoic acid. Number 6, from esters. Acidic hydrolysis of esters gives directly carboxylic acids while basic hydrolysis gives carboxylates which on acidification give corresponding carboxylic acid. Here you can see in this reaction ethyl benzoate is forming benzoic acid plus C2H5OH and ethyl butanoate is forming butanoic acid plus again ethyl alcohol. 12.8 Physical properties. Aliphatic carboxylic acid up to 9 carbon atoms are colorless liquids at room temperature with unpleasant odors. The higher acid or wax-like solids and are practically odorless due to their low volatility. Carboxylic acids are higher boiling liquids than aldehydes, ketones and even alcohols of comparable molecular masses. This is due to more extensive association of carboxylic acid molecules through intermolecular hydrogen bonding. The hydrogen bonds are not broken completely even in the vapor phase. In fact, most carboxylic acid exist as dimer in the vapor phase or in the aprotic solvents. Simple aliphatic carboxylic acids having up to 4 carbon atoms are miscible in water due to the formation of hydrogen bonds with water. The solubility decreases with increasing number of carbon atoms. Higher carboxylic acids are practically insoluble in water due to the increased hydrophobic interaction of hydrocarbon part. Benzoic acid, the simplest aromatic carboxylic acid, is nearly insoluble in cold water. Carboxylic acids are also soluble in less polar organic solvents like benzene, ether, alcohol, chloroform, etc. 12.9 Chemical reaction. The reactions of carboxylic acids are classified as follows. 12.9.1 Reactions involving cleavage of OH bond. Acidity. Reactions with metals and alkalis. The carboxylic acid, like alcohol, evolve hydrogen with electropositive metals and form salts with alkalis similar to phenols. However, unlike phenols, they react with weaker bases such as carbonates and hydrogen carbonates to evolve carbon dioxide. This reaction is used to detect the presence of carboxyl group in an organic compound. Here you can see all the three reactions where the 2RCOOH plus 2Na is forming the sodium carboxylate. RCOOH plus NaOH is forming the RCOONA, where CO negative and Na positive, and again the same product it is forming with the NaHCO3, and along with that it is also forming H2O plus CO2. Carboxylic acids dissociate in water to give resonance stabilized carboxylate ions and hydronium ion. Here you can see this resonance. For the above reaction, the K equilibrium constant and K alpha is the acid dissociation constant. Here you can see the both values. For convenience, the strength of an acid is generally indicated by pKa value rather than its Ka value. pKa is equals to minus log Ka. The pKa of hydrochloric acid is minus 7, whereas pKa of trifluoroacetic acid, that is the strongest carboxylic acid, benzoic acid and acetic acid are 0.23, 4.19, 4.76 respectively. The smaller the pKa, the stronger the acid, the better it is as a proton donor. Strong acids have pKa values less than 1. The acids with pKa values between 1 and 5 are considered to be moderately strong acids. Weak acids have pKa values between 5 and 15, and extremely weak acids have pKa values greater than 15. Carboxylic acids are weaker than mineral acids, but they are stronger acids than alcohols and many simple phenols. The pKa value is approximately 16 for ethanol and 10 for phenol. In fact, carboxylic acids are amongst the most acidic organic compounds you have studied so far. You already know why phenols are more acidic than alcohols. The higher acidity of carboxylic acids are compared to phenol can be understood similarly. The conjugate base of carboxylic acid carboxylate ion is stabilized by two equivalent resonance structures in which the negative charge is at the more electronegative oxygen atom. The conjugate base of phenol, a phenoxide ion, has non-equivalent resonance structure in which the negative charge is at the less electronegative carbon atom. Therefore, resonance in phenoxide ion is not as important as it is in carboxylate ion. Further, the negative charge is delocalized over two electronegative oxygen atoms in carboxylate ion, whereas it is less effectively delocalized over one oxygen atom and less electronegative carbon atoms in phenoxide ion. Thus, the carboxylate ion is more stabilized than phenoxide ion. So, carboxylic acids are more acidic than phenols. Effects of substituents on the acidity of carboxylic acid. Substituents may affect the stability of the conjugate base and thus also affect the acidity of the carboxylic acids. Electron withdrawing groups increase the acidity of carboxylic acids by stabilizing the conjugate base through delocalization of the negative charge by inductive and/or resonance effect. Conversely, electron donating groups decrease the acidity by destabilizing the conjugate base. Here you can see that electron withdrawing group EWG, that is, stabilizes the carboxylate ion and strengthens the acid. And here you can see that electron donating group destabilizes the carboxylate ions and weakens the acid. The effect of following groups in increasing acidity order is pH is less than, iodine is less than, bromine is less than, chlorine and is less than fluorine, then after less than CN and then less than NO2 and it is less than CF3. Thus, the following acids are arranged in the order of increasing acidity based on pKa value. Here you can see that order. Direct attachment of groups such as phenyl or vinyl to the carboxylic acid increases the acidity of corresponding carboxylic acid, contrary to the decrease expected due to the resonance effect shown below. This is because of greater electronegativity of sp2 hybridized carbon to which carboxyl carbon is attached. The presence of electron withdrawing group on the phenyl of aromatic carboxylic acid increases their acidity, while electron donating groups decreases their acidity. Here you can see that the 4-methoxy benzoic acid pKa value is 4.46. Benzoic acid pKa value is 4.19. 4-nitrobenzoic acid pKa value is 3.41. Now 12.9.2 reactions involving cleavage of COH bond. Formation of anhydride. Carboxylic acids on heating with mineral acids such as H2SO4 or with P2O5 give corresponding anhydride. Ethanoic acid is forming ethanoic anhydride. Esterification number 2. Carboxylic acids are esterified with alcohols or phenols in the presence of a mineral acid such as concentrated H2SO4 or HCl gas as a catalyst. Here you can see in this reaction RCOOH plus R-OH is forming RCOOR- plus H2O, and that is a reversible reaction. Now mechanism of esterification of carboxylic acids. The esterification of carboxylic acid with alcohols is a kind of nucleophilic acyl substitution. Protonation of the carbonyl oxygen activates the carbonyl group towards nucleophilic addition of the alcohol. Proton transfer in the tetrahedral intermediate converts the hydroxyl group into OH2 group, which being a better leaving group is eliminated as neutral water molecule. The protonated ester so formed finally loses a proton to give the ester. Number 3, reactions with PCl5, PCl3 and SOCl2. The hydroxyl group of carboxylic acid behaves like that of alcohols and is easily replaced by chlorine atom on treating with PCl5, PCl3 or SOCl2. Thionyl chloride SOCl2 is preferred because the other two products are gaseous and escape the reaction mixture, making the purification of the products easier. RCOOH plus PCl5 is forming RCOCl plus POCl3 plus HCl. 3RCOOH plus PCl3 gives out 3RCOCl plus H3PO3. RCOOH plus SOCl2 gives out RCOCl plus SO2 plus HCl. Number 4, reaction with ammonia. Carboxylic acid reacts with ammonia to give ammonium salt, which on further heating at high temperature give amides. For example, here you can see in this reaction CH3COOH plus NH3 is forming ammonium acetate, and then after on heating it is forming CH3CONH2. In the next reaction you can see that how the ammonium benzoate is forming, and then after the final product is the benzamide. First the ammonium phthalate, and then after it is forming the phthalimide, and then after on a strong heating it is removing one NH3 from it and forming phthalimide. 12.9.3 reactions involving COOH group. Number 1, reduction. Carboxylic acids are reduced to primary alcohols by lithium aluminum hydride or better with diborane. Diborane does not easily reduce functional groups such as ester, nitro, halo, etc. Sodium borohydride does not reduce the carboxylic group. RCOOH forming in the presence of LiAlH4 or ether or B2H6 forming it as RCH2OH. Number 2, decarboxylation. Carboxylic acids lose carbon dioxide to form hydrocarbons when their sodium salts are heated with soda lime, that is NaOH and CaO in the ratio of 3:1. The reaction is known as decarboxylation. Reaction is RCOONA. In the presence of NaOH and CaO on heating it is forming RH plus Na2CO3. Alkali metal salts of carboxylic acids also undergo decarboxylation on electrolysis of their aqueous solutions and form hydrocarbons having twice the number of carbon atoms present in the alkyl group of the acid. The reaction is known as coal-base electrolysis. Unit 13, Class 11th. 12.9.4 Substitution reaction in the hydrocarbon part. Number 1, halogenation. Carboxylic acids having an alpha hydrogen are halogenated at the alpha position on treatment with chlorine and bromine or bromine in the presence of small amount of red phosphorus to give alpha-halocarboxylic acids. The reaction is known as Hell-Volhard-Zelensky reaction. Here you can see this reaction, that is RCH2COOH in the presence of halide or red phosphorus and H2O, it is forming alpha-halocarboxylic acid. Number 2, ring substitution. Aromatic carboxylic acid undergo electrophilic substitution reactions in which the carboxyl group act as a deactivating and meta-directing group. They, however, do not undergo Friedel-Crafts reaction because the carboxyl group is deactivating and the catalyst aluminum chloride Lewis acid gets bonded to the carboxyl group. Now you can see here how this benzoic acid is forming the meta-nitrobenzoic acid and meta-bromobenzoic acid formation also with the help of benzoic acid. 12.10 Uses of carboxylic acid. Methanoic acid is used in rubber, textile, dyeing, leather and electroplating industries. Ethanoic acid is used as solvent and as vinegar in food industry. Hexanoic acid is used in the manufacture of nylon 6,6. Esters of benzoic acids are used in perfumery. Sodium benzoate is used as a food preservative. Higher fatty acids are used for the manufacture of soaps and detergents. Summary. Aldehydes, ketones and carboxylic acids are some of the important classes of organic compounds containing carbonyl group. These are highly polar molecules, therefore they boil at higher temperature than the hydrocarbons and weakly polar compounds such as ethers of comparable molecular masses. The lower member are more soluble in water because they form hydrogen bonds with the water. The higher members, because of the large size of the hydrophobic chain of carbon atoms, are insoluble in water but soluble in common organic solvents. Aldehydes are prepared by dehydrogenation or controlled oxidation of primary alcohols and controlled or selective reduction of acyl halides. Aromatic aldehydes may also be prepared by oxidation of number 1 methyl benzene with chromyl chloride or CrO3 in the presence of acetic anhydride. Number 2, formylation of arenes with carbon monoxide and hydrochloric acid in the presence of anhydrous aluminum chloride. And number 3, cuprous chloride or by hydrolysis of benzyl chloride. Ketones are prepared by oxidation of secondary alcohols and hydration of alkynes. Ketones are also prepared by reaction of acyl chloride with dialkyl cadmium. A good method for the preparation of aromatic ketones is the Friedel-Crafts acylation of aromatic hydrocarbons with acyl chlorides or anhydrides. Both aldehydes and ketones can be prepared by ozonolysis of alkenes. Aldehydes and ketones undergo nucleophilic addition reactions onto the carbonyl group with a number of nucleophiles such as HCN, NaHSO3, alcohols or diols. Ammonia derivatives and Grignard reagents. The alpha hydrogens in aldehydes and ketones are acidic. Therefore, aldehydes and ketones having at least one alpha hydrogen undergo aldol condensation in the presence of a base to give alpha hydroxyaldehydes, that is aldol, and alpha hydroxy ketones, that is ketol, respectively. Aldehydes having no alpha hydrogen undergo Cannizzaro reaction in the presence of concentrated alkali. Aldehydes and ketones are reduced to alcohols with NaBH4, LiLH4 or by catalytic hydrogenation. The carbonyl group of aldehydes and ketones can be reduced to the methylene group by Clemmensen reduction or Wolff-Kishner reduction. Aldehydes are easily oxidized to carboxylic acid by mild oxidizing reagent such as Tollens reagent and Fehling's reagent. These oxidation reactions are used to distinguish aldehydes from ketones. Carboxylic acids are prepared by the oxidation of primary alcohols, aldehydes and alkenes by hydrolysis of nitriles and by treatment of Grignard reagent with carbon dioxide. Aromatic carboxylic acids are also prepared by side chain oxidation of alkyl benzenes. Carboxylic acids are considerably more acidic than alcohols and most of simple phenols. Carboxylic acids are reduced to primary alcohols with LiAlH4 or better with diborane in ether solution and also undergo alpha halogenation with Cl2 and Br2 in the presence of red phosphorus, Hell-Volhard-Zelensky reaction. Methanol, ethanol, propanone, benzaldehyde, formic acid, acetic acid, benzoic acid are highly useful compounds in industry. And now this chapter is done. Thank you so much.